So thanks for having us. This is timely as we're just about to roll out some of our results for Whatcom County. And this was made available by the support of the City of Bellingham, the Port of Bellingham, Whatcom County, and City of Blaine to really help us do the final modeling of these impacts at the scale of Whatcom County. And since then, we've gotten some other partners, King County and several tribes. So we'll be filling in most of Puget Sound. And it benefits from a fantastic team of modelers, oceanographers, engineers, and work with international colleagues, as well as Ian Miller and Nicole and Bridget from Washington SeaGrant. And this is just an example of that video from Birch Bay in 2018. And the concern is really sort of more and more of this coastal flooding. And so what I want to talk about briefly is coastal squeeze and what we mean by that, how CoSMoS is going to address it. And so what is CoSMoS? How it's been used in California, where it's really the only location where it's been fully implemented and jurisdictions have been able to use it. And then what we're doing here in Whatcom County, some of the initial uses, and then how we're building in another component for dealing with the rivers of Puget Sound. So 16 or 19 large river systems with an example from the Nooksack. And then I'll just summarize at the end. So you've all heard, I think, terms like coastal squeeze. And what we mean by this is, sea level rise coming up from offshore, storm surges and waves related to sea level rise, being intersected by large river flows and flooding from above, and sort of squeezed between, urban uses, which constrain how water flows. And we're starting to see this a lot more frequent. The projections, I'm not going to go into the details other than say Ian and I and others have published an assessment of sea level rise forecasts for Washington State. And most of the climate impacts group work shows projections for larger river floods, potentially more frequent or more longer duration floods. And this is an example from a couple of flooding instances along Rotor and the lower Nooksack. And so what CoSMoS does along the marine shorelines is help advance the influences of dynamic processes like coastal storms and waves that add to flooding extent and other impacts along shore associated with waves that can erode things and move things beyond what the previously available tools were, which really were built on sort of static assessments of potential sea level inundation from sea level rise alone, which you see on the left versus the added influence of waves that you see on the right. And it'd be good to know how long it takes to update, because sometimes I talk too quick when I advance the slides, but hopefully the next slide is up, showing one of the tools that our team at the USGS has used to visualize these results. And it's called Our Coast, Our Future. And you can go to that and see all of the outputs from California. And it enables some interactivity for looking at different types of storm scenarios, tide positions, and then sea level positions. And I'll just sort of mention this, but it's a nice viewer for seeing sort of what is exposed to the different model outputs that we generate. And then more recently, we've been integrating with another USGS team with Nate Wood's group to provide what's called this hazard exposure and reporting analytics, HERA, and it's a socioeconomic component. And we're bringing all of this to Whatcom County at the end of this calendar year. So we'll have a lot of this for our domain here. And to summarize how folks in California have been using it, dozens of cities and counties for updating their local coastal programs, hazard mitigation and climate planning. Caltrans, which is the real large sort of user with a pretty sophisticated and large budget to maintain commerce and infrastructure. They've been using it extensively. California Coastal Commission for evaluating permits going forward in the future. A number of integrated sort of state climate change guidance and then county level guidance. I guess this is an example from one of the power plants, energy power plant. The ports have been using it extensively, including the Port of San Diego. It's been quite exciting. And then more recently, and really the bottom line is just last month, the California State Legislature used CoSMoS and HERA to justify passing this $3.7 billion climate change resilience spending package that you may have heard about in the news. So it's kind of like cross-cutting a lot of the different needs society has and emerging examples of sort of all the different ways folks are using it. So then what are we doing here? So we're modeling CoSMoS across all of Puget Sound and really British Columbia, the coastal British Columbia, the Salish Sea area, and this area in this blue, light blue color, trying to account for sea level rise, tides, ocean swell, and various sort of variability to water level that occurs out in the ocean, but then can penetrate into the Salish Sea. These are things like El Nino and the blob and other interannual variability. And then really modeling how winds and atmospheric pressure modify locally generated waves as they would sort of intersect all of our coastlines, and then including the fluvial discharge of all the rivers, including the Fraser. And so this generates one of our best estimates of the water level surface across this whole area. And we've been validating against all the tide gauges of NOAA, as well as a number of new tide gauges that we installed and have been operating for 2 years, as well as wave gauges to validate all this modeling. And for the water level, we're getting our error down to under 10 centimeters on average at all of our locations, which is pretty exciting. And then what we do is we couple that with a wave model also spanning the whole area, and together model the past with a 35-year hindcast, as well as the future using global climate change models and various ways of downscaling them spatially to compute waves at the scale that we need them, which we think are on the order of 100 to a couple hundred meters across most of the domain. And then what we're doing, and so that's a regional scale, and we've completed all of that. And now what we're doing with partners like Whatcom County and the city of Bellingham and the port are bringing it to county scale reaches of the shore by then modeling how those waves and water levels rush up the shore and lead to either overtopping or flooding and what have you. And we do this by recently transitioning to a really neat new approach, which is a very computational efficient 2D flood solver that takes the outputs of this water levels and waves offshore, the run up, and computes where that water is going to flow. So it's a very nice physically based approach rather than in the past often using a GIS approach. And just a couple things to add is that we are adding a regional groundwater model of sort of the annual average position of the groundwater this year and simulating how sea level is going to be influencing that groundwater to cause groundwater flooding. And then next fiscal year, in fact, we've already started, but we are working on how to then incorporate local rainfall and its infiltration in order to then compute the runoff from pluvial processes, so rainfall driven processes, which will really kind of add most of the flooding risk that we care about up here. The outputs are going to be output at 1 meter resolution. And these are maps and GIS data layers directly to our partners, as well as this web viewer with statistics and representation of the flood extent, the depth of water over the land, the duration of these floods that occur, the flow velocities of the water over the land that gets flooded, and then wave heights offshore for sea level rise of various increments going forward. And they're shown here. They pretty much span the range that we think can occur this coming century, as well as sort of some real extreme numbers like that 5 meter and 3 meter that we're uncertain about, but want to capture in case it happens in the future. And then we're going to be looking at a number of different types, defining different recurrence interval events. So the 1 year flood, 2, 5, 10, 50, and 100-year flood events. And then this exposure to groundwater flooding, which you can see most of this on that California web viewer as examples, and then the HERA. So for Whatcom County, we're just finishing the last sort of refinements to the modeling and outputting these results. And so I'm going to show you a few examples of just the downtown urban area. For example, what we characterize now as the 100-year flood event with 1.5 meters of sea level rise. And you can see an example of these colors and semi-transparency indicating water depth over land with this particular event. And an example of the duration of one of these types of 100-year floods in the future in hours, colored darker purples, and then water velocities predicted for areas that it floods. And then I'm going to show you a few other examples and then sort of describe how we think and have heard from our partners and others how it will also help inform things. The other way to look at it is also positions of sea level rise and the difference between different types of recurrence events simultaneously, so you can kind of think about planning and different risk tolerances or risks that are suitable or acceptable. So these are just, again, some examples. It's been interesting now going through this exercise and computing storms like what we've noticed and seen. For example, that 2018 Birch Bay kind of flooding and what happened at Semiahmoo. And so here's again some examples. And so what I wanted to stress is that this is going to be really useful to planning harbors, parks, ecosystem restoration, general adaptation planning. But what I wanted to bring up is, so for example, on the left is sort of the current 100-year flood. We've really not known how to put one of these events into the context of that recurrence, extreme recurrence, because we really haven't had the approach for modeling the joint occurrence of all these processes. And so it's interesting to sort of see some of this validation in terms of photographs and compare it to the model which predicts a 100-year event, causing something like what we observed, even though we only have a record of 30 to 50 years of sort of measurements and then people's historical representation of what may be a large event or not. So this has been helpful for a lot of jurisdictions to put large extreme events into some context of recurrence. For Birch Bay, a number of you have seen what happened there, as well as a few more times. There's been some flooding and impacts. And so here's some of those examples, and they agree pretty well in terms of the current position of sea level rise, what a 100-year coastal flood extent would be. And we're using Birch Bay, in fact, as a validation point for the modeling. And then you can start seeing what an extra 0.5 meter or 1.5 meter of sea level rise might do to that same type of 100-year flood event. And we wish we would, have finished this, or the Birch Bay berm was sort of in a phase maybe a couple years out, so we could help inform it. But one thing that's going to be really useful is once the berm has adjusted and the sort of final morphology is sort of reached, the county will be mapping it in high resolution, and we can then plug that into this CoSMoS model and evaluate what the new sort of morphological berm may be able to mitigate in terms of those future flood events. So it's interesting. We're sort of in a place where we can help adaptive management and planning. We're doing a real similar thing with other projects. For example, a restoration of a clam garden with Swinomish. We can run the model now with a new set of configurations for a clam garden and see to what extent that clam garden will help mitigate some of those projections of future flooding and wave impacts. Moving on to sort of another real important issue is, how we're going to go about planning for a lot of very vulnerable coastal properties and residences, and in particular armoring. At some point this might get pretty severe, and the armoring that we currently use may not serve us. And so, the CoSMoS really helps examine sort of the risk and exposure and maybe thresholds where, we're all going to want to sort of see a different type of sort of level of protection and approach to protection. One last example is the city of Bellingham with the Post Point water treatment plant. They're in a stage of planning out sort of additional capacity. And so CoSMoS has been able to begin informing some of the sort of forecasted changes in the area and where there may be sort of more suitable areas for some of that expansion. And so this has been exciting to be part of and help inform. Again, just an example of a large storm surge event with some of our projections of future sea level positions to give the city some idea of exposure in the future. And then just a couple slides, how am I doing on time? A couple slides about how we're going to deal with rivers and river deltas, where the localized impacts of the river flooding are really critical, and sea level rise is already influencing those types of flooding. So we have a new compound flooding approach, and we've been building this out in the Nooksack and the Nisqually so far, and have been asked to do this in the Snohomish. It's accounting for all the effects and then that joint probability of river floods with high tides and storm surge. And this is just a quick example of what the model looks like. It's very high resolution over the floodplain, where we're interested in knowing how floods will flow across the landscape. In this case, we have a really nice set of validation along the river and on the floodplain. And this is what it looks, let's see. This is an example of the Super Bowl flood of 2020 at Slater Road. You can see the extent of flooding on the eastern levee and floodplain. It was pretty impressive. And here's what the model looks like. It takes a couple minutes to get to where there's some action, but here's the tides going up and down in black, and then the river discharge ramping up to that peak of the flood on February 7th, I believe it was. And you can see the effects of tides pushing water up in the Smuggler's Slough and up on the floodplain. And then somewhere real quick here, everything sort of breaks loose at Hovander Park and down a lot of that eastern floodplain that you see. And so this is the first time we've been really modeling the dynamic, continuous nature of the tides and the storm surge meeting the river, as opposed to sort of a scenario-based approach. And our accuracy is really exciting. We're within about a foot of the flood peak in the river and the floodplain, which was suitable to the flood district. And then quickly, what is exciting about these models is you can really then manipulate the forcing to examine other flood events and future changes to floods, as well as restoration alternatives. And so this is the first part of that. It's looking at the past and analyzing how well the model performed for the Super Bowl flood, which I just sort of got done showing. The water depths, in fact, were real comparable to the measured maximum water depths. And then we were able to look at the 2009 flood, which is a larger 25-year event, and see, in fact, that it captured the flooding that was observed on the west side of the river, which it did exceed some of the levee tops. And what's exciting is to be able to, assess the vulnerability to what's being projected for the future. And so on the left is the 2040s, the right is the 2080s, the top is sort of the middle 50% likelihood of change, and the bottom is the sort of unlikely but higher potential extreme change that both Ian and I put in the sea level forecasts, as well as the climate impacts group with Guillaume Mauger is projecting for the river flood increases. And the numbers we used are shown here. We're revising this bottom one to more like 60%, but we're waiting for another model input to use that. But it's pretty clear that once we get into these higher flows and sea level, there's going to be a need to really adapt how to protect some of these environments or accommodate the flows. But here's the exciting part, is there are a number of really exciting habitat restoration opportunities that in fact reduce that flood exposure. This is just one particular one that we've evaluated so far that's on public lands, connecting the that eastern bank across the floodplain to previous historic channels that used to flow through here, and reducing the levee somewhat. And what it showed us is that if this alternative 3 in the comprehensive river management plan was in place during the Super Bowl flood, it would have reduced the maximum stage by almost 2 feet in this area here, and had a benefit moving upstream several kilometers and downstream. This is really exciting. And so the natural question was, well, what about, will it benefit those future flows? And so we ran the same modified bathymetry for this alternative 3, and found that there was a benefit to reducing the flood all the way through the 2080s, even with that sort of 1% increase in river flows and sea level. So it's exciting. It buys the community some decades to really plan out the best strategy. And this is just one alternative. There may be that several alternatives reduce that, that impact or exposure even more. And so lastly, this has all been about flooding, the MRC, and a number of other groups interested in salmon and estuary recovery. We want to see other sort of metrics and model outputs. And so what I just want to say is that in modeling everything that I've shown you so far to get the flooding outputs, there's completed models of the waves over time, their wave heights, periods, the wave energy, the storm surge magnitudes, frequencies. Those are all ready to be now used in derivative analysis or additional analysis to look at things like the fate of sediment coming into the system, coastal morphology changes, things like beach habitat suitability that we might examine with LUMI, effects to armoring, when that sediment gets out and waves are churning it up from the bottom, the light availability for kelp and eelgrass and what have you. look at the effects of wave resuspension of the bed material today, as well as how much it might change in the future. And I bring this up because we're in fact coupling a lot of the coastal habitat change work that I've been doing in the past with CoSMoS to evaluate some of these questions, like how does wave resuspension today under these large events potentially move some of the legacy contaminants that are out in Bellingham Bay, and how will these projected changes in the future with sea level rise and wave energy influence that? And so this is an example of what we're learning today. This is sort of the average hours of bottom sediment mobility for the material that we find on the bottom. So muddy material offshore, sandy material up close to shore, in terms of the hours per year based on a 5-year continuous record in the recent period. And so you can imagine extending this with all those CoSMoS models of waves rushing up the beaches and hitting the bluffs. We're in a good position to start analyzing a lot of really important sort of habitat, geomorphology, and other metrics I think that you all think about probably more. And so these are all sort of ready to go in sort of a phase 2 CoSMoS for ecosystems, let's say. And so I'll just sum up saying this new coastal storm modeling system, projections of the combined influence of sea level rise, storms, waves, and stream flooding help inform exposure to flooding and wave impacts. Many areas along Whatcom County that have showed are pretty vulnerable to flooding and wave impacts today, and they certainly become more with sea level rise. The compound flood modeling in the river deltas shows sort of a really rapid increase in flood exposure due to the increased sea level positions and the projections of increased stream flooding. But there's really exciting opportunities where habitat restoration is going to help mitigate those effects. And then the coastal storm and wave modeling that's been done as part of this project has a wealth of other data for us to go back into and start extracting and using in additional analyses to evaluate coastal habitat change, things like the likelihood for erosion or the migration of marshes and beaches and what have you. So that's what I wanted to share today. Final results are coming out at the end of November. And it's going to be exciting for you all to sort of chime in on sort of how to use it, how to advance it maybe for other things you're interested in. So thank you. I'll turn it over to Ian and maybe have questions after Ian's, or now, whatever you guys want.
Either or. Also, if people have questions and you're afraid you're gonna forget them, feel free to put them in the chat too.
Yeah, you know, while it's fresh in everyone's mind, a couple of questions would be totally fine if there are any outstanding.
Does anyone have any questions?
I guess just a quick question. I was just glancing at the HERA tool online and I noticed I heard you say it's only right now for California and that's all that it is. Okay.
Once we have our first outputs for Puget Sound, which are really Whatcom County, thank you, our partners, then they'll start, we'll have those at the end of the calendar year.
Oh, great. Okay, thanks.
I have a question about how the data is going to be shared. You said results will come out end of November. How is that going to be disseminated?
Both through HERA. So okay. The exposure will be through HERA, and then we're devising this approach to serve the data layers, and you'll be able to download them there,
okay,
as well as being shared directly to the city, port, and county. Okay. Typical GIS data layers, what have you.
And my other question is, and maybe you mentioned this and I missed it, but and perhaps it's already incorporated into the modeling, but so this is a lot about stream flooding, but what about the flip side? What about, decrease in snowpack and decrease in snow melt and less water coming down? I mean, how is that getting folded in?
So this is really focused on those extreme high water
Yeah.
flood events. We are not currently looking at those real low flow events, but certainly the modeling that we're doing in the rivers,
Mhm.
which is sort of like CoSMoS for marine shorelines versus CoSMoS for rivers. Those models are suited for looking at low flows and changes in sort of wetted area. Yeah. Take it away, Ian. Hey,
Okay,
buddy.
well, I'll go ahead and so I'm Ian Miller again with Washington SeaGrant, and you know, so what I'm going to focus on today is actually not directly CoSMoS related, although we're honored to be partnered with USGS SeaGrant, a variety of folks from SeaGrant, and we'll be focusing on sort of you know, really engagement and community applications of CoSMoS in the coming years. But based on Kurt's kind of initial invite to me, I am focusing this presentation, it's going to be hopefully be short, maybe 10 or 15 minutes, on the question of, you know, what do we know about the vulnerability of nearshore habitats to sea level rise? And this is actually based on another project that I'm engaged with that's a near-term action that I'll describe a little bit about, but partnered with Jim Johannesson and Avery Maverick from Coastal Geological Services, Bellingham-based firm, and then Chloe Fleming and Sean Regan, who are with NOAA's NCOS, which National Center for Coastal and Ocean Science, I believe is the acronym there. And they're based in other parts of the country.
Hey, Ian.
Yeah.
Ian, this is Claire. I have my speaker on maximum and you're sort of
Oh, no. I
quiet.
was wondering if my audio was gonna work here. Let me see if I can mess with that on. Does that help at all?
Yep.
Okay. Let me know if, let me know if that is another problem. I'm using a headset that has been suspect in the past. So, so this particular project that we're engaged with is, again, a near-term action. It's called Prioritizing Sea Level Rise Exposure and Habitat Sensitivity Across Puget Sound. So, and this is really, in my mind, a follow-on to the sea level rise projections that we published in 2018 that Eric alluded to, that some of the CoSMoS modeling will be connected to. But here, what we're really trying to get at is less about, you know, exactly where is water going to go, and it's more about trying to assess vulnerability to future sea level, and which gets at, you know, what is going to be touched by that water and what is its sensitivity, and you sort of couple those to get at vulnerability. And we are trying to do this at the scale of individual parcels along Puget Sound. So to sort of give you another sense for what we're trying to achieve with this, I'm showing you a stretch of developed shoreline here. This is on the Dungeness River Delta on the Strait of Juan de Fuca. But if I switch the slide here, you can see the results from a project that was the pilot, or the sort of the progenitor of this NTA that we're doing currently, which was a couple of years ago, in which we created a quantitative index for sea level rise vulnerability, which that we can then map on the landscape with the intention that we can identify those coastal parcels or those areas of the landscape that are most vulnerable. So here we're moving beyond exposure, you know, what's flooded, to what's on the parcel. And for this project and for the NTA, we're trying to consider both the built infrastructure on the parcel, which is sort of the typical and traditional way of evaluating vulnerability. And because we are in Puget Sound and we acknowledge that, you know, we value coastal habitats, we are also trying to assess the vulnerability of those coastal habitats. So when Kurt asked, you know, what can we sort of make some comment on how different sorts of nearshore coastal habitats may respond. What I'm drawing from is primarily research that we did to try to figure out a way to assess the vulnerability of those habitats for this project. So just a little bit more about the project. Again, it's funded through Puget Sound NEP restoration funding, and then we've got this support now from NOAA NCOS. It's a small project. Those of you that work on NTAs, you know, they're typically small. Our project team is made up of 5 people, and we're all a fraction of FTE. So it's really kind of pilot or experimental in nature. But again, parcels are our fundamental unit of analysis. So we're trying to come up with a quantitative index for every parcel. And we expect it to be done and published, at least this, what I consider to be a first phase in the middle of 2022. Now we are trying to do the entirety of Puget Sound. So every parcel in Puget Sound, the intention is to score it. So we have a set of data criteria. This is a data-driven project, right? This is not new field work. This is reliant on public and published data sets. And the data sets have to be current, 2010 or later. They have to be public, freely available online, and they have to be regionally consistent. We're not going around and building up data sets from pieces that different counties have, for example, or different jurisdictions have. Okay, so I'm leaving out a bunch of detail about how we assessed exposure, how we're assessing infrastructure sensitivity, to dive right into the habitat elements, because that was the key point of interest. So, you know, one of the things we want to do within this project is score habitat sensitivity, which essentially what we're trying to get at is there an important coastal habitat on or near a parcel along Puget Sound? And then how sensitive is it to sea level rise? So as sea level rises, how do we expect that habitat type will respond? And so I'm going to present to you some summaries based on our review of approximately 30 papers or data reports that we reviewed to try to get at this question for coastal habitats in Puget Sound. We ended up sort of classifying or focusing our attention on, 3 habitats. They are very broad in general, and we decided on that because we needed continuous coverage of habitat types for all of Puget Sound. So we ended up using NOAA land cover data, which doesn't map, you know, here's kelp. Instead, it maps broad classifications like shallow aquatic vegetation, for example. So I'm going to go through the 3 of them that we are sort of focusing on in this project. And then I'm also going to address a 4th that was a particular area of interest in the email that Kurt sent me initially. But first of all, we lump kelp and eelgrass, sort of submerged aquatic vegetation, if you will, sort of the shallow aquatic photosynthesizers. Those are one group in our sort of data framework. There's some literature though that's separate, focused on each. There tends to be more for eelgrass than there is for kelp. But generally what we found is that the literature points to a fairly low sensitivity of eelgrass and kelp to sea level rise. And this is because, well, there's a variety of reasons, but migration shoreward is likely for both of these groups of, one algae and one plants. The consequence of that, where it has been modeled, and there's a couple of sort of nice papers out there, some of them by people that you likely know. John Risbick, for example, is based at Western Washington University. I've done some work modeling possible sea level rise responses for eelgrass and Padilla Bay, for example, and found interesting results suggesting, for example, that areas of eelgrass may even expand in those environments. It's really dependent upon what the sort of the upper intertidal elevations look like in those environments. So there are some locations where, vegetation area may actually increase as a consequence of sea level rise. So local vulnerability is really associated with those places where migration is blocked, both for kelp and eelgrass, we think. We find, again, this very low sensitivity of these two groups of shallow aquatic photosynthesizers to sea level rise. But we note that sea level rise is probably not the primary climate associated stressor. So again, I just wanted to emphasize that we're focused here on sea level rise vulnerability, but both of these groups of shallow aquatic photosynthesizers probably are sensitive to other climate drivers, notably water temperature and potentially water chemistry. And we do not assess how they may respond to that. Those two things may certainly stress these groups of shallow aquatic photosynthesizers. So the next class that we looked at is what we broadly define as coastal wetlands. And really, this is sort of a broad definition that's inclusive of upper intertidal vegetated areas. So both backshore, beach backshore environments. This photograph that I'm showing down here is from the Elwha Delta, showing sort of a typical sort of beach backshore environment, or these kind of salt marsh environments associated with some of the large deltas and some of the accretion shore forms in Puget Sound. So these, based on this literature review, these sorts of vegetated, backshore and marsh environments, these coastal wetlands are sensitive to sea level rise. They are expected to respond to sea level rise, but they have two mechanisms by which they can respond in ways that would allow them to persist. Either they can accrete vertically, so if the landforms on which they grow are able to sort of move vertically, then those plants essentially can keep up with that vertical accretion. And then the other is they can migrate landward. So they have these two mechanisms of adaptation. The evidence that we reviewed suggested, I should also point out that for these vegetated coastal wetlands environments, there's some really interesting work emerging out of the East Coast that suggest that there are other feedbacks that these sorts of environments, especially marshes, can use to persist through sea level rise. So that's encouraging news. It's still somewhat hotly debated, but encouraging news about the potential enhanced sort of resilience of these kinds of vegetated backshore environments. So back to the original two mechanisms, though, that we sort of identified for these kinds of vegetated habitats. Literature for Puget Sound generally points to sort of relatively rapid vertical accretion rates, especially for the marsh environments. So we sort of assess that our primary sensitivity is driven by the ability of these habitats to migrate landward. So for our project, therefore, we sort of said, hey, if there is room to migrate landward, then we assign these sorts of habitats a relatively low sensitivity to sea level rise. If there is no room to migrate, though, then there's a chance they may not persist as sea level rises, so a moderate sensitivity. And the final group of the final habitat we looked at was beaches. So these are sort of unconsolidated, sediment shorelines. These sorts of habitats, which are important, in Puget Sound, are important for especially forage fish and obviously sort of aesthetic and recreation potential for people. Generally high probability of persistence. And this is very similar to those coastal vegetated habitats, if migration space and sediment supply is available. Unlike marshes, for example, for Puget Sound, we generally sort of assume there's a low sediment supply for beach maintenance. So that led us to conclude that beaches have a moderate sensitivity if there's room for them to migrate. If there's not room for them to migrate, if they're blocked, then they have a high sensitivity. So, so the translation there is, as sea level rises, it's likely that this habitat type goes away if it cannot migrate. And of course, the sort of barrier to migration that's of most concern, at least as an anthropogenic stressor, is armoring. And so this is kind of the typical coastal squeeze that Eric alluded to in his presentation, where you have a beach fronting armoring, and as sea level rises, essentially that beach can't respond. And so it essentially disappears as an intertidal habitat. So in our project, we're trying to assess, because we sort of determined that migration is our primary criteria associated with sensitivity. Our sort of task at hand is to try to assess if and how these habitats can migrate. So we are using a tool that is actually freely available online. It's part of the NOAA Sea Level Rise Viewer. This is what we're using currently, which is a marsh migration tool that NOAA published. I'm just going to show you sort of an example here. This is the contemporary distribution of some of these mapped habitats that I described to you. Again, these are the broad categories. So this is a partial legend on the side here for some of the habitat types that I just focused on in the previous slides. And then this is I believe a 3 foot of sea level rise scenario. This tool responds to this in the same way the NOAA Sea Level Rise Viewer does, in the sense that you have a slider that you can select different sea level scenarios. This is an elevation-driven tool, so it simply says if there's adequate elevation on the landscape, and these habitats will move into it. So we're then coupling that with armoring data that's been collected for Puget Sound, primarily by Coastal Geological Services. So building that into this, adding those as barriers to assess where these habitats cannot migrate as a consequence of those barriers. So I don't have any results to present to you yet, because we're not yet done with the analysis, but to give you a sense for sort of how we're assessing the sense and how we're sort of relatively ranking the sensitivity of those coastal habitats. That was really kind of my point. The final comment I wanted to make was about shellfish beds, because there was Kurt illustrated particular interest in the email that was sent about shellfish beds. We are not specifically assessing these in our project, mostly because we don't have any region-wide data on shellfish beds that we can incorporate. However, a couple points that I'll pull out that are mostly based on work that I did for the Olympic Coast National Marine Sanctuary that we published in 2013. It was a climate change exposure assessment, essentially, for a variety of coastal habitat types and species of concern in the sanctuary that was inclusive of some shellfish species. So drawing from that, just a couple of points in regards to the sensitivity of shellfish for sea level rise. Generally, a lot of these species have high reproductive potential, so they're spawning every year essentially, and they're also broadcast spawning, so reasonably successful at moving their location. So that this high migration potential gives them a relatively low sea level rise sensitivity, right? We assume that if adequate habitat is available at a higher elevation, they can occupy it fairly rapidly. However, this is, again, like eelgrass and like kelp, other climate-related stresses are likely far more important for something like shellfish as compared to sea level rise. Sea level rise is not the thing that's going to get them, essentially. It's going to be something more like, obviously, acidification or water temp or air temp. This photograph at top was taken on the east side of Marrowstone Island shortly after the June heat wave. I'm guessing you guys saw stuff like this around shorelines in North Sound. These are cockles that did not survive that combination of a low tide and very warm air temperatures. And so that's likely a bigger driver for climate-related sensitivity for these organisms than sea level rises. So just a couple notes, sort of like summarizing what I just went through, but would be happy to sort of talk and discuss more, or sort of talk about how we're trying to implement this into our NTA.
Well, thank you so much, Ian and Eric. We still have time for questions if there are any questions. I see that Kathy put a question in the comment box and Eric followed up on it. Are there any other questions? Alan, I see your hand up. Alan, if you're trying to speak, you're still on mute.
Okay, sorry about that. Do you feel sufficient confidence in the results to be able to influence jurisdictions to remove community responsibility for risks to habitat, to infrastructure or housing development that blocks migration? And I'm thinking also that in your sea level rise, you need Eric's wave action too, because that's part of the factor that increases the migration capability, I guess.
Yeah, let me try to address that. So I guess first of all, for the last question, 100% agree. For this near-term action project, we actually had to build our own inundation layers that were derived from, from our 2018 sea level rise projections, and then coupled with kind of our own extreme water level assessment. But in the future, CoSMoS will make that process easier for us. And so hopefully in future iterations of, similar sort of like quantitative vulnerability assessments for sea level rise in Puget Sound, we'll be able to draw on those CoSMoS layers. Save us a bunch of time, gives us more accuracy to work with. So that would be very desirable, but the timing didn't work out for this particular project. So do we have enough confidence about, especially, I'm assuming you're referencing sort of like efforts to remove armoring in Puget Sound. And, do we have enough confidence to sort of maybe use the argument associated with habitat blockage as a reason to remove armoring? Is that kind of, I'm guessing that's kind of what you're after?
No, it's somewhat related, but I'm thinking more about right now, you can't prevent people from doing stupid things. And FEMA and the like, emergency disaster relief, helps all those people that build on bluffs and build in flood areas. So I'm just wondering if there's enough in this to move the dial on some of the zoning issues.
Yeah, I mean, my take is that there is, but it's a slow process, and it's a slow process in Washington, especially because we are a state in which many of our coastal management decisions are pushed down to counties and cities, essentially. And so, every county and city and tribe, for that matter, they essentially sort of are making their own decisions to a degree about if and how they will address sea level rise in their planning processes. I think one of the fundamental, ideas about how, people like Eric and myself are approaching this is that at the very least, what we can remove are the technical information barriers that have been presented previously to communities when it comes to planning. So by way of example, when I first got into this, it was in 2012. and it was a project that I was involved with the Jamestown S'Klallam tribe, in which they had to hire a consulting team to sort of derive some localized relative sea level projections for their community. It was something they had to find funding for, and it was a project. What we did in the Washington Coastal Resilience Project in response to that and the 2018 sea level rise projections that Eric referenced is we essentially created those for everybody, right? So nobody anymore hopefully has to hire a consulting team to come up with that kind of information. They just go grab it. So that's kind of where we're putting a lot of our energy now. Now that doesn't get us as far as we need to go, because communities can still choose to not incorporate it or incorporate, everyone sort of goes about it in different ways. So it's not ideal to address the problem that you highlight, but we are further along now than we were, even a couple of years ago.
Thanks. Oh, are there any more questions?
I have a question. Does the model include geological rise or fall of the land over time?
So let me take that first, Eric, because we've got two different models here. We have this kind of quantitative vulnerability assessment that I described, and then CoSMoS. And I'll let Eric address CoSMoS, but for our sort of quantitative vulnerability assessment, yes, it does. Every single parcel on Puget Sound essentially has a different relative sea level projection associated with variability in vertical land movement across Puget Sound. And that is built into the inundation layers that we've built for this project. So, the sea level rise projection for Bellingham is going to be a little bit different in our GIS model than it is for Olympia for a particular time and a particular likelihood.
Yeah, and similarly, Mike, ours are, I may have gone through it pretty quick, but what we're trying to do is model discrete intervals of essentially the effects of sea level rise. And we do incorporate the vertical land motion across the whole domain, but how it gets factored into someone like yourself is through the timing that we expect that amount of sea level rise to happen. And so we're going to develop this essentially a tool that crosswalks the model outputs we're generating for CoSMoS to the sea level rise assessment that Ian mentioned. And you'll be able to sort of work across and define the timing that quarter meter of sea level rise or half a meter of sea level rise is expected to occur in your local area, because we downscaled all that. And the benefit of all this is that as we are learning about new science coming out, that the rate of sea level rise might increase or accelerate. We don't want to redo all the modeling for a particular time in the future, but we can just simply cross-reference our existing models to sort of the new time in the future that amount of sea level rise is projected to occur. Hope I said that clear enough, but
just as
so it does incorporate those changes in elevation. Say the coastal areas versus Puget Sound might be different, and so that incorporated into the model.
Yeah.
Okay.
Okay.
In fact, the example I was going to throw out was, CoSMoS will sort of provide you with an inundation layer for a 100-year storm event after a quarter meter of sea level rise. And we'll have that output for, let's say, Nia Bay and Port Townsend, and you can look at those maps, both for a quarter meter of sea level rise. But that scenario of a quarter meter of sea level rise is going to happen a lot faster in Port Townsend than it does in Nia Bay. Yeah. So you have to interpret it relative to when you expect that amount of sea level rise to occur. Because Nia Bay is uplifting rapidly and Port Townsend is subsiding.
And that's what we want to do the next few months, is work with folks like you to make that real clear how to do it, how to look at our CoSMoS results and then our 2018 sea level rise assessment and see those differences. So we'll work on something for that.
Are there any other questions? All right, well, thank you so much for presenting to us tonight. And one of the advantages of Zoom, while it's really nice meeting in person, is that we can have people like Ian Miller, who doesn't have to drive for hours to get to us to give a presentation. So we really appreciate you guys joining us tonight. And I know I have been following your research, and so it's really always fun and interesting to see updates and how things are progressing. And it's really exciting to see it kind of scaling down more to the local level. And here in Whatcom County, I think we selfishly are really excited that CoSMoS is happening here. And Ian, we also appreciate all of your work too. We look at, you know, habitat and other things like that. And so it's really great to learn a little bit more about what's going to be more vulnerable as sea level rises. So thank you so much. And thanks for joining us. You're welcome to stay for the rest of the meeting, but I also know you two are super busy people. So no hard feelings if you decide to sign off, but thanks for joining us.